Gas exchange in fish. What is the structure of fish gills? How is water passed along the fish gills? What is the difference between parallel and countercurrent flow? How does countercurrent flow increase the rate of exchange? So fish have a waterproof and gas-tight outer covering, and because they're large, or relatively large, they have a small surface area to volume ratio, and therefore their body is not enough to supply and remove respiratory gases on its own, so they've developed specialised exchange surfaces, which are the gills. So looking at the structure of the gills are located behind the head, and they're made up of gill filaments, which are stacked up like pages in a book. At right angle to the filaments are gill lamellae, which increase the surface area of the gills. So water is taken in through the mouth, flows over the gills, and goes out through the opening on each side, which is called the operculum. That you have the gill arch. You've got the gill rakers, and if you feel them, they are quite tough and quite sharp. And then you have the gill filaments, which are stacked up on top of each other like pages on a book. And then at right angles to that is the gill lamellae, which increase the surface area for gas exchange. So the flow of water over the lamellae and the flow of blood within them are in opposite directions, and this is known as the countercurrent flow. And it's important for maximum possible gas exchange, because if they flowed in the same direction, then less gas exchange would actually occur. So looking at the countercurrent exchange principle, this is the direction of water flow, and this is the relative concentration of oxygen. And then this is the direction of blood and the relative concentration of oxygen. So you can see that water flows in one direction and blood flows in the other. So the countercurrent exchange principle is where blood and water flow over the gill lamellae in opposite directions. And that means that blood that is well loaded with oxygen meets water that has its maximum concentration of oxygen, because this water has only just met the lamellae, whereas this blood has already picked up most of the oxygen. However, the water still has slightly more oxygen than the blood, so diffusion will occur. So diffusion occurs from the water to the blood across the whole length of the lamellae. So at the other end, blood with little or no oxygen meets water which has most of the oxygen removed, and therefore there is always diffusion of oxygen from the water to the blood. So therefore there's a constant rate of diffusion across the entire length of the gill lamellae. So you can see here that the water the saturation of oxygen in the water is always slightly higher than the blood, but there is always a diffusion gradient across the whole length of the lamellae. So that means that 80% of the oxygen available in the water is actually absorbed into the blood. If the flow of water and the blood were in the same direction, which is known as parallel flow, the diffusion gradient is actually only maintained across half of the length of the gill lamellae. You can see here that the diffusion stops. There is no diffusion gradient after half the length of the lamellae. So it's actually only 50% efficient if the water and blood were to flow in the same direction in parallel flow. So maintaining that diffusion gradient requires both ventilation, so the fact that the water is flowing continuously through, but also a mass transport system.